My name is Quentin, and yes, so I'm a doctoral researcher at Tampere University in Finland, and my work is about how can we do like developmental robotics with DFT. It's a topic that is in progress. Lots of people are doing that, and I will show you a bit of what I'm working about and future work also in that domains. So today we'll talk about how can we go from sensory motor contingencies, so sensory contingency learning, to autonomous goal discovery. So a bit of research context behind that. The goal of doing that is to perform autonomous skill discovery in an open-ended learning fashion. That's a new field. I mean, quite new. Let's say 10 years old. Inspired by lifelong learning. So, of course, we discovered by while doing robotics, we can't specify every time just what the robot has to learn. So the idea is to take inspiration and see how babies and infants are growing and are learning by themselves, and try to reproduce that with robots. So it's challenging because we can't say what the robot has to learn. And in the field, actually, I didn't see anybody using DFT for doing that. I think there are some reasons, but I also think that DFT can also overcome some of the issues we are encountering in the domain. So it's inspired by lifelong learning. So how we grow up and how do we learn continuously. And as I said, it's instead of specifying what the robot has to learn, the robot has to decide autonomously what's it interesting for him to learn. So what to explore and what to continue learning. Some background about it. There's various way of doing like open-ended learning. Actually, the first one of the important work in the domain is the work about intrinsic motivation from Houbre, but there are also other people who worked in that. I think the first one was actually Jürgen Schmidt-Houbre in the 90s, where basically they use neural networks to perform any kind of learning, and they kind of the robot try to predict a lot of things, and if the prediction are getting more accurate over time, it means that some skills is getting like acquired. And more recently, of course, with the explosion of deep learning and particularly deep reinforcement learning, we've seen a lot of work about it. So I guess you all have, maybe you have heard about the work about playing Atari game and stuff like that. The thing is, this kind of techniques, you need like tremendous amount of data to work. And in terms of biologically inspired, it's not exactly how it, I mean, it's not how it works, but I mean, it still overcome like all the previous techniques. So it's still interesting to dig into that. And there are also work about goal-based learning, where the robot just generate goal, learn to reach goals, and continue with generating more complicated or high sensory goal, and so on. And it starts small and goes like bigger every time. The advantages for open-ended learning is, of course, you don't specify what the task is going to be. If you heard about like reinforcement learning, you know that you have a reward function. For example, if your robot learn to grasp like an object, you have a reward function that will evaluate like how good is he grasping or is he reaching towards the object. And but as I said, it's not going to be good if we want the robot to continuously learn. So we are not going to specify one reward after another. The good thing also, it can lead to like the emergence of behaviors. So since we don't know precisely, but we have an idea of what the robot is going to learn, sometimes it could lead to some behavior that we are not expecting. I put some literature at the end about it. So sometimes and that's how we also discover like developmental stages. So naturally, for example, the robot learns to touch objects before grasping it, or to move it before interact it more deeply with them, which can provide in some way some explanation on the developmental path that infants can follow. But the disadvantage right now with all the current techniques, so by intrinsic motivation, deep reinforcement learning and stuff, it's sometimes poorly inspired. For example, not a lot of people, or very few people, talk about the role of memory and attention, and how can different cognitive processes can interact together, and it's often also really complex architecture that can be seen as black box. So it's always like kind of policies, learning all together, and it's some complicated sometimes to, when you read some of the paper, you spend some time before understanding how really it's made. So the goal here is to use DFT to step down a bit the level of modelization. So instead of just having like observing the developmental stages and like propose an it's more like we observe the developmental stages. We look into neuroscience, for example, into learning, what exactly learning means, what are the process involved in terms of memory, working memory, and so on. And the idea is to get inspired by what we observe in neuroscience to propose DFT model in my case, and have more clear understanding, or let's say try to represent better how can we do open-ended learning in terms of skills. The idea is a lot of in this background is they try after and to like propose cognitive explanation about the algorithm and stuff, but they only come after that. They don't start beforehand with that to try to after propose some model that can do it. And that's my goal with DFT, is to start from neuroscience and see what kind of process are involved into open-ended learning. So in order to do so, I started by tackling the problem, the issue of learning sensory-motor contingencies. So in developmental robotics, this is a really early stage of motor action or motions. So this is, for example, what Piaget observed in terms of motor babbling. So basically, what children do, they often act and interact with the environment and perform gesture until seeing what kind of gesture is going to bring some results in the environment. Or what if I push this object? Oh, okay, I saw that this object is actually moving, so this motion is actually interesting for me. And according to the last principle and approach, we can see that cognition arises from the dynamic interaction with our environment. So the more the infant interact and the more we interact with the environment, the more we are able to learn and to update our belief about the world. Which is also really interesting in terms of embodiment, which is by linking together perception and motor experience, and also proprioception together. So it's not only because I saw something moving, but it's also the fact that touching it, doing that precise motion, that bring some information to my nervous system about the process involved. And of course, in this process, you have some homeostasis, what we call homeostasis, which is like all kind of self-regulation. So everything is influencing everything, and it's all turning kind of a closed loop. So the approach of this first paper was to propose a model where the robot is able to perform some motor babbling, and for the robot to observe like the consequences of the action and see what can he learn about that. And just by the simple process was just to perform motor commands and observe the results and associate them together. And by a simple model that is able to perform some exploration, so motor babbling, and perform some exploitation. So how can I use the knowledge I just learned to perform better action then? So to do that with DFT, how to represent and produce a sequence of action, I guess you already saw all the kind of model with intention, condition of satisfaction, and linking behavior together. But the problem is with that kind of approach, it's kind of discrete. So you either have to plan all the possible action to take before, and it can link like to really long chain of intention and action, which was not really suitable with what I wanted. I wanted to perform more in continuous action space. So I couldn't plan all of that in advance. And the setting of the experiments, I just took inspiration from like a famous baby mobile experiment where the researcher attached a string to a robot, to a baby mobile toy. And it's basically when you saw the birth of the sense of agency. It's basically when babies from the age of 2 months old begin to understand that their action have consequences. So basically by attaching the string to the foot, the baby is going to move the foot and is going to understand by moving the foot, it's going to move also the toy above him. And I think the setup of this experiment was simple enough to learn sensory motor contingency with the robot. So how to perform that? So first there is an exploration stage, which is the motor babbling. So how do we generate an action from neural fields? Basically really simple. I took inspiration from the inhibition of return effect that we can see in attention, for example, just to avoid generating the same action. And I have neural fields divided by action and states. So basically you have the states of the arm here, and you have the possible action to take. In that state, for example, you have all these possible actions to take. So you have like continuously represented actions, and the actions correspond to basically a motor angle from, I think it was from -1 to 1, which was like from for one motor from 90 degrees to 0, for 0 to 120 degrees. And this is just the simple model for exploration. So you can see we have here the generate action part, which is basically we have a slow boost module that I will present afterward, which would just slowly rise the resting level of a field. There is an action emerging from that field that project back to a memory. So that's where I keep track of the action already taken. And this is the inhibition of return mechanism where I project the action which has been performed into inhibition actually here. So which means we cannot, the model cannot generate twice the same action given a certain state. And so here we have the generate action. Once an action has been decided, it goes to a selective field, which then transforms to a motor intention. Here we have the memory part where I have a simple motion detector of the robot that just record how the toy is moving in front of it. And every time I generate an action and perform an action, I record into a memory trace the output of this action. So if the arm is going to move and it makes the toy moving, it's going to keep into memory precisely the effect of that action associating with the level of, let's say, motion from the toy is going to see. And so it transmits to the motor, of course. And you have, of course, motor states. All the fields you can see are always divided by states and action. So at any point, the state, which is let's say the proprioception, so the state of the motor is pan over here and is choosing an action. So here, by just boosting slowly the resting level of the field to make an action emerge from there. And once an action has been performed and observed, you have a condition of satisfaction field, which correspond of when the state of the arm is in the same position of the action that just happened. So that means my action is just over. So that means, okay, I can start to generate a new action again. And this is pretty much the exploratory behavior. So I generate an action, I observe the consequences, and I record the consequences into a memory trace. And we have the exploitation stage, because it's nice to perform motor bargaining, observing it, but that's where actually the learning occurs. It's how do I exploit this knowledge to perform a better sequence of action. So basically the exploitation motor of the arm, I will slowly raise the resting level, and depending on the action with the high consequences I saw here, it will kind of rise, it will rise the resting level, and like the highest peak at that state, which means that was the best action taken that brings the robot the best visual activation. So it's going to be to emerge, and into the selective field, we will stop to boost the resting level. And that means we are going to select that action, since it was the best one, to perform it. And we record them, that action, into, let's say, a final memory trace, where I will just have the best action taken for a given state. So basically, what it just does is I have a state, I see what's the best action. Okay, that was this one. I update the state. I see what was the best action. Okay, that was this one. And up, I go back to that state again, because here, that action there corresponds to that state here. And that's how I form, let's say, in time, in the experiment, form a stable sequence of motor commands. So for the first paper, we had like two, let's say, two action. Even if we explore quite many places, these two action was the one always like going to each other. So basically, the arm was going left and right all the time to make the toy move. So we did the experiment with a gummy arm, so which is like a 3D printed arm with a tandem as actuator, but actually mimic the human arm. So you can actually pull on it and stuff. You are not going to get hurt, which is interesting for other purposes. And this is the upper arm roll motor, which is like this one that actuates like the arm to go left and right here. And span, as I say, over the neural field. So the motor angle is from -1 to 1, which by just a simple coordinate transform, we span it over 0 and 100, and which is this neural activation are the same one as you can see here, actually just 3D one. And you can see like the highest peak are the action with the highest that brings the highest value when he saw like the toy moving in front of him. And in terms of results, so we launched like 10 experiments where we applied 10 exploration, and after we applied 10 exploitation. And the whole idea of the experiment is to see if this method of learning is actually good or actually working to learn sensory motor contingency. And how can we observe that? Since the vision here, the change acts as some kind of reward. So the highest we see, that means the highest, so the learning is actually occurring. So we can see by the exploration, the visual activation are all quite the same over all the experiment, but we can see the exploitation is slightly higher every time than the exploration. That means it chooses every time the best action. So it's logical that it's going to bring him the best outcome in the environment. And when we gather the 10 experiments over time, we can see the exploration phases of the visual reward you can get are really quite random. But when we apply exploitation right at the beginning, you always seek and always get the high outcome in the environment. I think it was important to talk a bit about coding because I guess you heard about CEDAR, even perform exercises with it. The robot is running with ROS. So I developed all kind of plugin for that. It's under my GitHub experiment. And I have this GitHub for this paper. So it's just to say it's really easy to interact with CEDAR. Either you use ROS or YARP. It's quite easy to continue. I think I will speed up a bit. We continue with another experiment where you can see we use the inhibition of return mechanism, but we wanted to see how it can influence the exploration of the sensory motor contingency. So what we did basically is just to modulate the strength of the inhibition of return. So that means when the action, I decided how strong am I going to inhibit them for later when I generate them. And we can see with a strong inhibition of return, the exploration space is more limited here and than with a weak one. Basically, with a weak one, it can explore everything. But with a strong one, basically, he inhibits a whole part of the field every time. That prevents him to explore other parts. And we explored it, and the result led to, for example, doing exploration, this is, it led to almost the same kind of graph than up there, but we could see that doing exploration with a strong inhibition of return, it led to almost directly to the same result than with the exploitation, which was interesting for our perspective, because after for the robot to explore, for exploring the motor space, it can lead to better exploration if he knows what kind of thing he can already try to explore. And this is like a simple graph. So we just measured here with the strength of, with a strong inhibition of return, we just measured the final sequence of action. So always the same action performed after the learning. And we saw that after the strong inhibition of return, it reached really quick, a steady sequence of motor command. With this weak inhibition, it takes more time to explore, and thus is not going to exploit the knowledge right away. And this is a motor intention field. So this is a motor command used doing exploitation. So with a strong inhibition of return, so he basically just explore and is basically just exploit left and right, but he explore left, middle, and right. And for the exploration with a weak inhibition of return, he basically explore everything, but during the exploitation, he's keeping left, middle, and right. which are almost the same result that the exploitation with the and the exploration here, which was interesting to observe. And now we have that. The problem is we don't have an autonomous way of switching between exploration and exploitation. So the idea here is to observe into neuroscience what kind of mechanism can allow us to switch from exploration and exploitation. When do I decide that exploring things are more important than exploiting my current knowledge? And by that, we inspired by recent discoveries where the role of basal ganglia in the brain actually modulates the exploration exploitation stages and experience, and that under certain condition, increase of dopamine decrease the exploration of new action. So we found it was interesting to model some DFT mechanism that would able to switch autonomously from one to the other because of an increase of dopamine. So what we explore here is like having moderate and regulate level of dopamine, reduce the exploratory behavior. And in other study, we also saw that the role of dopamine as a reinforcing signal. So when something nice is happening, you will have a release of dopamine also in the brain. So how can we put these two mechanisms? So always a small amount of dopamine at some point that would reduce exploration, and a bit of dopamine, let's say, when something interesting is happening in the environment. So we kept the same architecture with, this is still the same action generation mechanism with the inhibition of return. This is still the same exploitation, and this is still the same memorization. The only thing difference here is the switch mechanism. So basically, something interesting happening. So when my action is leading to good consequences, we have the vision field here that is going to project into a memory trace we call MEMT vision there. So every time I get a, let's say, reward from the environment, it's going to raise a bit this memory field. And every time I will perform an action, so either generating a new one or exploiting one, I will put just a bit of mimic the role of dopamine, just a bit into this empty state. So every time I will perform an action, depending on the states, I will have a small amount of, let's say, dopamine, but here it's modeled by a small amount of excitation into this field. And we are going to put these two fields together and project it into what we call the condition of exploration field. So that means when the condition of exploration, condition of exploitation. So when this field is going to activate at some states, he will decide by this mechanism here that is going to exploit his knowledge. And basically the condition of exploitation. So you have here the same field, which is all the action taken. So you can see here, it gave like, or in that state, it gave a small amount of excitation, just a bit every time. And here, this is the memory trace of just when a good action with high results was produced, which are produced both together, put together, gives this neural fields where he will decide, depending on the states the harm is, if he's going to exploit or not the knowledge. And basically, we can resume it with really simply. When a state has never been visited and no reward was actually observed, there's no peak of activation here on the state. And if a state was visited only a few times, but a high reward was observed during that state, so there is a peak emerging for there. And visiting a state multiple times without observing any reward will still produce a peak. It's the equivalent of saying, for example, that I did that many times I know it's not going to give much, so I'm going to exploit what I know. I'm not going to explore it further. And the result together leads to really interesting results. So the switch mechanism, we gathered 10 experiments together, and we saw that after a certain amount of time of exploration, it begin basically to exploit, and that's where it's going to gather with time more and more rewards. So where it will perform the action, meaningful action. And this is summed here by I have an exploitation node and an exploration node, so we can see which stage is at any time. And you can see that at the beginning is mostly exploring, and that after some point is beginning to exploit, which is here. We can see here the beginning of exploitation that leads to higher rewards every time. So we spoke about sensory motor contingency with only one harm, but we used only one motor for it. And how can we go from sensory motor contingency to goal learning and to formation of goal? And the idea about the future work is to go towards the learning of higher order goal. So instead of having, let's say, a visual a toy that moves in front of me, and I told the robot, of course, that he should observe that toy. No, it should form by itself the kind of goal he is going to observe. So the idea is to use a simple, simple in the process DFT mechanism, inspired by the work from Schneegan in terms of gain modulation, and inspired by the work of Mai in terms of still gain modulation, but they use also kind of model. So basically, if you have like a modality A, let's say touch, and a modality B, let's say sound, they are both projecting into a field there, and you can also perform the convolution between the two of them, which is going to be there, and you can perform some learning between the projection of both modality here and the convolution of them here. And the learning would occur into a 3D memory trace, right? Because when you associate a 2D field with a 1D one, you got like a 3D one. And the idea is to have the learning there. And in this memory trace, we would have the representation of two goals, for example, of touching something and hearing a sound together, and a particular peak inside this memory trace would represent a special modality, would represent these two modalities, but as really what you just observed with the robot. And the idea with that is you can also combine it, for example, with another modality, let's say vision, and have another learning. And basically in this 3D memory trace, you would have like the modality touch, vision, and sound all together. That could represent goal, for example, touching a blue ball that sounds funny could be represented there. And by using this kind of model, you could theoretically build higher and higher goals and represent, let's say, yes, complicated, not complicated, but let's say complex situation. And but this doesn't answer the question of how do we avoid to precise, for example, a reward, or what kind of modality to observe. And the idea here is to inspire from the 3 layers architecture that you can find in from Johnson, but also in the DFT book. I didn't ask permission, but I had the reference here from the figures. Basically, these 3 layers can act as a novelty detector. So when you have a peak appearing here. You have here working memory forming, and with the inhibition, I think, yeah, coming back, you can see that if I first encountered like a modality, for example, if I just heard a sound, it goes into memory and inhibit it. That means if I see it, if I hear that sound again, it's not going to raise the peak here. I think you can observe that into the experiments with the spatial hypothesis from Linda, from the A not B error into children. And so this would act as a novelty detector, and putting that with that, we can actually have the novelty detector detecting like a new goal. And depending on the goal observed and how complicated is the goal, we can actually put that together to see how new is my goal. Okay, I already see it, so it's not interesting. Or I'm going to search for a new one, and which would lead to the formation of complete goals and the sequence of it. And of course, we still keep in mind the exploration and exploitation process that we are going to integrate with these two ideas, where I will explore for new goal, and if I don't discover anything new, I will exploit the one I already know to discover a new one. And this is the idea of how we can, I mean, the idea of, but I imagine how can we perform some learning without specifying what to learn with DFT, because DFT is really useful for the modelization of higher cognitive process. And I think with this kind of things, and also by modulating a lot of parameter, you can observe a lot of different behavior emerging. So the idea is to play with that to see. Interesting to talk just a bit about the code. I mean, not the code itself, but since we are in Corona situation here in Finland, we are working remotely, so I can't have my robots at my place. I mean, I didn't ask, but no. So the idea is to work with simulator, and just to say how easy it is to, for example, integrate the iCup simulator to Cedar. So it's just a simple plugin here. It took like 10 lines of code, not even, to get like the image that the robot is perceiving, and you can see you can integrate it really well into the neural fields here, and already play with a novelty detector, for example. So all the plugins I coded are available. And for example, I coded a lot of plugins to make interfaces with ROS. And this one works with YARP, because YARP is natively built with CEDAR. So you can also use them to use DFT to control the end effector of the iCub. So which is really funny to play. You just have a peak of activation and you move the hand everywhere just by moving the peak of activation, which is quite fun actually to do. And I think I don't have time anymore. I plan to show just a bit of demonstration of the slow boost mechanism, but only if I have time. Well, thank you very much. And I have the, of course, I will publish. I will give the presentation, so you can have access to all the references I was talking about.
I think we have a little bit of time, if that's not a huge, a very long demo.
Okay, so I have, it's really simple. It's just to show, I already had the, so the slow boost module I told you is just to raise slowly the resting level to see how can we see the emergence of an action, or to generate an action. So it's really simple here. So this is like the slow boost mechanism here. You will see it just going to start. I have 3 entries. Basically, it will raise the resting level of the selective field here. And when the selective field has a peak, it goes back to the slow boost to say stop raising the resting level with that. And the two other entry here is just to reset the boost mechanism. Here, I just did it really simply because I don't have my robots, because it will I will need a condition of satisfaction to stop it. And since I don't have my robot to verify which states I'm going to do it manually. So just by saying, okay, let's do that. See, the resting level is rising and I have an action coming. Which seems to be a big one, but if you had a convolution, for example, it can act as some kind of filtering. So the huge peak you can see here will just transform into a small one centered at like the 25 position, for example. You can see we can induce a new one. Up, and this one is over there. So it never gives, this is like, let's say not the instability, but non-determinist, let's say, action of the neural fields that makes it always take a new action. And by the inhibition of return, for example, if I record this action here into memory trace and inhibit it, it will never select it again. So at some point, if you record all the action, you will have inhibition everywhere at all kind of place where you already took action. And it would not be possible to select a new action again. So yeah.
So this slow boost mechanism, is that an algorithm? Or is that some kind of neural?
No, actually the slow boost can be seen as zero-dimensional memory trace with a low, not sigma, I don't remember the parameter. The memory trace is like the pre-shape with a low time scale build. So it can be seen like this. I just decided to code it this way because in my experiment, the pre-shape sometimes can bug, and also I needed to have control over the slow boost to stop the experiment if I needed to, or to pause it, or to have a better control of the architecture.
Yeah, I see.
And also with the slow boost, I have two parameters. I can set up a limit when to stop the boost, and I can also set up like a boot step. So this is the equivalent of the time scale build, but with the simulation time, I thought it was more easy actually to set up a boot steps, or how many steps by second is going to increase.